Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore the concept of change in velocity. Now we know that the algorithm for change in velocity is delta v equals vf minus vi, where delta v is the change in velocity, vf is the final velocity, and vi is the initial velocity, often given the symbol u. Now the key thing to understand is that when we're dealing with change in velocity, we tend to be dealing with vectors. We're looking for the vector which is going to promote the change. What is going to cause the initial velocity to change into that final velocity? Now obviously as we go further on in this unit, we'll express the idea that if we're going to have any form of change in velocity, we're going to have to apply a force. Newton's second law, F equals ma, states that if we're going to change the velocity, i.e. accelerate an object, we're going to have to apply a force onto the object at a specific direction, which is going to promote that change. And we'll explore a little bit more of that in this video. Now note that in this case we've got Vf minus Vi. Now the minus Vi when we're dealing with a vector means that we've got to change the direction of that initial velocity. And again that will become apparent later on. So let's look at this scenario. Well, we've got 3 meters per second down below. We've got a vector going to our right. We also have a vector going north at 2 meters per second. So we've gone 3 meters per second this way, and then somehow there has been a change at 2 meters per second. Now that change, which has caused that 3 meters per second going to the right to go straight up, basically has been denoted by the change in velocity, and that is shown by the green arrow. Now what we've got to actually combine together is the idea that the initial velocity and the final velocity must combine to promote and equal that change in velocity, because obviously all of the three sides of the triangle have to meet up. If the change in velocity is of a specific size, then the final velocity or the initial velocity are also going to be the same. So as a result, we're going to have to see what's going to cause that change in velocity. And this is the way that we go about it. So basically what we're going to do is look at the change in velocity in one dimension, and then we're going to look in 2 dimensions and hopefully give you the tools that will allow you to go away and practice these. I'm then going to produce some exemplary videos which will show you how you can utilize these and then produce a worksheet that you can actually practice. Okay, so the first thing that we've got to do if we've got a change in velocity in one direction is basically find our vectors. So we've got 2 vectors here. We've got 5 meters per second going south is our initial velocity, and then we've got 2 meters per second north, which is our final velocity. The change in velocity has caused our vector going 5 meters per second down suddenly changes it, so it's going 2 meters per second north. So how do we do that? Well, the first thing is we follow the algorithm. We write down what our final velocity is. Now our final velocity in this case is 2 meters per second north, our pink arrow. We then have to put in our initial velocity. Now our initial velocity was 5 meters per second south, so we put that in. But hang on a sec, because what it says is it's negative Vi. So as a result, I've got to change the direction of the initial velocity. So instead of going south, I'm going to have to go north. So you can see now that I've changed my initial velocity, so it's going in the opposite direction, still the same magnitude, but it's going in the opposite direction. So I've got 2 meters per second north, and I've got 5 meters per second north as well. So they're all going in the same direction. Now, I join up the 2 vectors, and that's going to be the resultant. Now, because the 2 vectors are going in the same direction, I can solve it simply by adding the 2 together. So the change in velocity from converting 5 meters per second south into 2 meters per second north, I have to apply 7 meters per second in the northerly direction. So as the 2 directions are in the same way, I just add them together. Obviously, if they were in the opposite directions, I would take them away. So the key thing to understand about change in velocity is it's the vector which causes the change of one vector into another. So I hope that makes sense. So you follow the rules accordingly. If you follow this 5-step sequence, you won't go wrong. Just making sure that when you get to your initial velocity, you change the direction and then solve the equation accordingly in 1D. Okay, well, let's have a look at what happens when we're looking at two directions or two dimensions. So in this case, we've still got our same algorithm. The vector change in velocity equals the final velocity minus the initial velocity. I then have my two vectors. I've got 2 meters per second north is my initial, and 3 meters per second east is my final. So I do exactly as it says in the algorithm. I've got to write down my final first and then do my negative VI. But let's have a look first at what's actually occurring in this scenario. I'm going 2 meters per second north, then I go 3 meters per second east. So something must have caused that change in direction or change in velocity, change in speed. Now my speed has actually increased and my direction has changed as well. This is because of a vector acting somewhere on the outside. So I was going this way, something pushed it to push it in this way and accelerate it and speed it up. What is that vector? That is your change in velocity. So by using the algorithm, we can calculate what the magnitude and direction of that green arrow is. So I write down VF. So VF is 3 meters per second east. I then add in VI, noting that I've got to change the direction. So if I put in VI, which is 2 meters per second north, I then have to change its direction, so it's now going 2 meters per second south. Now you'll notice that I've top and tailed each of my vectors, just like we saw in our previous vector video. You'll notice now that if I take the tail of the yellow arrow and join it to the head of the pink arrow, it's going in exactly the same direction as the green arrow in my scenario just above. That means we're going in the same direction. The length of that arrow basically will be the magnitude. So I can join up these two vectors and find my resultant, which is the change in velocity. So now what I've got to do is solve the equation. Now you can see I've got a right angle triangle here. This allows me to basically use Pythagoras and trigonometry to determine what is the magnitude and the direction of that green arrow. So we get a right angle triangle, as you can see here, 3 meters per second east, going 2 meters per second south, and my green arrow basically is working at an angle X and has a length which we're just going to call a question mark. So to calculate delta V, to that change in velocity's magnitude, I've got to use Pythagoras, and basically it's the square root of 3 squared plus 2 squared. This comes out at 3.6 meters per second. So that's the magnitude of the change in velocity. Notice that all of the vectors here all have to have the same units. But I haven't finished there, because remember we're looking at change in velocity, so I need a direction. So that change in velocity is acting at a specific direction. What is that? Well, that angle is X. So we can find X by 10 to the negative 1, or tan to the negative 1 of 2 over 3. Basically it's opposite and adjacent, hence it's tan. Opposite is 2 divided by the adjacent, which is 3. Solve the equation, I get 33.7 degrees. So combining all that together, I get an overall change in velocity of 3.6 meters per second east, 33.7 degrees south. So that's where the change in velocity is acting. Well, I hope you found that useful. Remember that these are the sorts of scenarios that we are going to be dealing with, not only with velocity, but we can do this with any form of vector. So anything which has got a vector link with it, for example, force, we can then apply the same rules. So we need to practice these skills for one dimension and then 2 dimensions, and then later on we can then look in 3 dimensions. So start having a go at those practice questions. I've also put up some exemplary videos which hopefully will work you through various stages of different questions, getting more complex as we work through. Okay, well, I hope you've enjoyed this video and you found it useful, and I look forward to you joining me again. Bye for now.